This video will be going over section 3.3, which is on solving trig equations with identities. So this really builds on section 2.3 that we did in this class, which was solving basic trig equations, which were just equations with a single sign or a cosine in them. We talked about how to get the two smallest solutions or two solutions within 0 to 2 pi, and then we talked about getting the general solution. So really all we're going to do here, if you built a good foundation in that section, then what we're doing in this section isn't going to be much more. It's really just going to be an acknowledgement of realizing if we have powers of trig functions, if we have multiplications of trig functions, you can probably factor or use the quadratic formula to solve them. And then in the last part of the section, we will actually use identities to solve them. And we'll talk about the things you have to be wary of when you are solving trig equations. Right, so I just have outlined here what we did before, kind of what I said. We'll really be focusing on finding all the solutions between 0 and 2 pi. In this section, we don't have the questions asking for the general solution, but remember, if you wanted to do that, it was pretty easy once you got to the end. Once you figured out all your solutions between 0 and 2 pi, you just add the period times whatever letter you are told to use. Right. So very often when you see equations with powers of trig functions or sines and cosines multiplied in the same equation, you will solve by factoring. And if you cannot factor, the quadratic formula is something you can use as well. Many people like to solve these questions by replacing cosine of t or cosine of whatever your variable is with an x and sine of t with a y, because thinking back way back to the unit circle, that's really what they represent. It also helps to realize, if you do this, why we have to solve them the way that we do. But the important thing is that you end up solving the equations for your variable t. Right. So number one here says solve 15 times sine of t times cosine of t equals -3 sine of t. All right. So what I'm going to do, just to kind of explain why we have to do it the way we do it, I'm going to do exactly what I did up here, or I mentioned up here. Replace cosine of t with x and sine of t with y. So this would kind of read as 15 times y times x equals -3y. Now, one of the main things about what we wrote up here is factoring, or using the quadratic formula. You know, if you're going to do either one of those things, you need to make one side 0. And for all these questions that we're going to do, for the most part, some we might be able to not have to get 0 on one side, but for the most part, you need to get zeros, or not zeros, just 0 on one side. And that really follows from the fact that when you use either of these two things, methods, factoring, quadratic formula, you get 0 on one side. So I'm just going to kind of work this one with y and x just to explain what we're going to do. I think also factoring with two variables, that's something you should be familiar with. So what we would do to get 0 on one side is adding 3y to each side would do it for this one. Okay. And once we get 0 on one side, the first question I always want to ask, factoring, if we can do it, you want to do that and not worry about the quadratic formula anyway. But this isn't something we could use a quadratic formula on because there's no x squared or y squared. So we really have to factor. And the greatest common factor here, we have a y in both terms. And on the numbers, our numbers are 15 and 3. And we can take a 3 out. You can take out a 3y. And when we factor that out, we take a 3 out of 15, we get 5. The y is gone. The x is still inside. Plus, when you take a 3y out of 3y, you take the whole thing out, you get a 1 plus 1 equals 0. Now, what I want to do at this step, since we're not actually solving for y and x, but we did the factoring part, is I'm going to plug back in and actually work the rest of the problem out down here with our actual sine of t and cosine of t. So after you're done factoring, after you're done using the quadratic formula, it's a good idea to plug back in what we did. So we got 3. In place of y, we use sine of t. Then we got parentheses. You can write brackets if you don't want too many parentheses, just to make it look a little nicer. 5 times x, which is cosine of t, plus 1 equals 0. And the whole idea with this, solving this, is now once you have it factored, and you have something factored and it's set equal to 0, you do exactly what you did in college algebra ever since you started factoring. We set each one to 0. Meaning we have the stuff out front, 3 sine of t equals 0. And we have the stuff inside, 5 cosine of t plus 1 equals 0. Yeah. And really the whole point here, what's happening is now this becomes like 2 problems from section 2.3, and you know how to solve each of these. Right. So we're going to try to get, since we want it on the interval 0 to 2 pi, we want to try to get two solutions for each. Right, and then whatever our solutions are, combined, are going to make up our final answer. Right, it's just like when you factor and you set each factor equal to 0 and you get all the solutions for each part, they all make up your answer. Right, so the one on the left, 3 times sine of t equals 0. If you divide by 3, we just got sine of t equals 0 here. And now the angles that make sine equals 0 are 0 and pi. Right. The angle 2 pi also makes sine equals 0, sine of 2 pi equals 0, but we don't include 2 pi in our answer because it's not a part of what we want. Right, but these you can get because sine of t is the y value on the unit circle, y is 0 on the x-axis. The two angles for that are 0 and pi. Now this is going to be 2 of our answers. You can leave them like this. You can write them as decimals. It doesn't matter. If you can give exact solutions, you can just leave them exact. If you want to type in pi and get a decimal, you can, but it's probably just best to leave it like this. Now we solve the other one. We know what to do with this. We got to get the cosine of t by itself. So we got 5 cosine of t equals -1. Then we divide each side by 5. And we have cosine of t equals -1/5. And then we ask ourselves the question, can we figure this out on the unit circle? The answer to that is no. We have no idea what angle makes cosine -1/5. So what we got to do is we got to use our calculator, do the inverse of each side. And we know from past experience solving questions like this, there's going to be two answers. We might as well point out what quadrants are cosine. Is cosine negative in? Cosine is negative in quadrants 2 and 3. All right, so I'm just going to draw our picture here and put in an angle representing our answer in quadrants 2 and 3, and then we'll actually find them. Right, exactly like we would have done before. We're going to have 1 in quadrant 2, 1 in quadrant 3, and we can use our calculator to start getting one of them. So we get t equals cosine inverse of -1/5. Once again, from the way they want our answers between 0 and 2 pi, you want to make sure you're in radian mode. So we got cosine inverse of -1/5. And you get, well, that's probably in degree mode. Yep. All right. 101 does not look like something that would be in radian mode. All right, so just press enter again, and we get 1.7722. All right, remember, we're going to use this answer to get our other one. So it's a good idea to round it farther than you need to. But this is our quadrant 2 angle. Right? 1.772 is in quadrant 2, not quadrant 3. Now, also what we learned back then is that the reference angles have to be the same here. So if we can figure out the reference angle, we can figure out our quadrant 3 angle. Our reference angle would be pi minus 1.7722. Remember, the bigger of the two angles, bigger minus smaller. We know this one in pi, so we compute it like that. We get pi minus 1.7722. We get 1.3694. Since we now know that reference angle is the same, our angle in quadrant 2 here would be pi. Since it's beyond pi, it's pi plus 1.3694. Let's go ahead and compute that. And you get 4.511. Right, but that gives us our two answers between 0 and 2 pi. Right, quadrants 1 and 4 are where cosine's positive, is not going to have any answers. It's only negative in quadrants 2 and 3. So for this part of the equation, we get t equals 1.7722 and 4.511. Once again, the whole point of this section, not every trig equation you're going to ever need to solve in a calculus class, for example, is just going to be one single sine or one single cosine. What you need to acknowledge is that you can probably factor and solve it some way. Right, but this has 4 answers. We got 2 for the one on the left, we got 2 for the one on the right. You can have, really for these kinds of problems, you can have 2 for each thing that comes out of factoring. You might not have 2 every time, which we'll see examples of, but you can have up to 4 answers if you get 2 equations from factoring. Okay. So let me just go ahead and write in to make it more clear that these are our final answers. And just read the directions of how to type them in. All right, so that one, I guess I should mention, you're not, like I said at the beginning, you're not going to use a quadratic formula when you do something like this with a sine and a cosine, because the quadratic formula, the purpose of that is if you have an x squared or a y squared and you can't factor it or don't know how to factor it. So the next one says solve 8 sine squared of t minus 2 sine of t equals 1 for all solutions between 0 and 2 pi. Same exact directions. And we immediately again want to think about factoring or using the quadratic formula. And I'm going to start doing the same thing I did last time and replace here, since we have sine of t, with y. Now it looks like we're solving 8y squared minus 2y equals 1. All right. Once again, either one of these methods requires us to have 0 on one side, so we need to get 0 on one side. All right, you subtract the 1 on each side. We get 8y squared minus 2y minus 1 equals 0. And a lot of the problems in this section, because of the way they need to form answers, you're going to have to be comfortable with at least checking that you can factor something without a 1 on the front. But we can factor this. There's a lot of ways, to factor something without a 1. You can do the AC method, you can guess and check. There's the box method, there's a whole bunch of stuff. The reason I know I can factor this is because if we multiply a times c, which is 8 times -1, we get -8. And we can find two numbers that multiply to -8 and add to -2. That would be -4 and +2. Now you can also use that to know how to factor it. One thing I would just point out here, because you have a -1 at the end here, you're going to have a 1 on each. One's going to be a minus and one's going to be a plus. And then think about what numbers can I put in here. Of course, they're going to each have a y, but do I do 8 and 1, 4 and 2, 2 and 4, 1 and 8? Since we've got a -2 here, I'm thinking about putting a 4 that would go with the negative and a 2 that would go with the positive. So when I FOIL that out, it'll work out. Right. So we can factor that, and we did. And I'm going to proceed exactly like I did last time. Now that we factored it, I'm just going to plug back in y equals sine of t and continue to solve. The one thing I always recommend with plugging back in, you don't want to plug back in before you factor, but at least if you plug back in right after you factor, you don't forget what you're actually solving for, which is t. Right, so we got 2 times sine of t minus 1, and then we got 4 times sine of t plus 1 equals 0. Same exact thing as last time. We have two things factored and multiplying and set equal to 0 now. So now we set each equal to 0. We got 2 times sine of t minus 1 equals 0. And 4 times sine of t plus 1 equals 0. And just solve each one. Now, these are both questions that you could have been asked back in 2.3 as well. All right, so the one on the left over here, you add 1 to each side, we get 2 sine of t equals 1. And then we divide by 2, we get sine of t equals 1/2. And once again, this is something you can do by hand because we know where the trig functions sine and cosine are 1/2 on the unit circle. You can also still use your calculator and round if you prefer. But since this is knowledge about the unit circle, I'm going to do it like this. Our two answers would be pi over 6. Sine is positive in quadrants 1 and 2. Reference angle is the small one for 1/2, which is pi over 6. And the other one would be 5 pi over 6. Just like last time, this is going to be 2 of our answers. It might end up being the only 2 answers. It might be that there's 1 more. It might be that there's 2 more. We just got to solve the other one and see. Right, but now we solve the other one. We subtract 1 from each side. We got 4 times sine of t equals -1. divide the 4 on each side, we get sine of t equals -1/4. And then we ask ourselves, do we know where sine of t equals -1/4? Unfortunately, we do not. So that's going to be something we have to use our calculator for. I'm going to make a picture so we can visualize everything. All right, we can go ahead and record what quadrants is sine positive in, or negative in rather, with negative in quadrants 3 and 4. So we're going to have an answer in quadrant 3 and an answer in quadrant 4. And I'll go ahead and draw a sample angle for each one. Now, we know what to do from here. To start by getting one of the answers, we do sine inverse of each side. And we get t equals sine inverse of -1/4. Once again, we're in radian mode. And we do sine inverse of -1/4. We get -0.2527. Gonna round one spot farther, just like last time. And now this is the one that always was a little messier to solve, but we know this is in quadrant 4 because it's barely negative. It's between 0 and -π/2. So this is our quadrant 4 angle. It's just not between 0 and 2π. Okay, so remember what we've got to do is we've got to add 2π to it. Make sure it's between 0 and 2π, but in the same spot, coterminal. All right, so we can do that in our calculator, and that'll be one of our answers. I'm just going to do plus 2π because that's the last thing I typed in. And we get 6.031. So one of our answers is going to be 6.031. Now, in our other answer, we need the reference angle for. But we talked about doing reference angles with this quite a bit as well. The reference angle would be just this angle, but not negative. Right? The thing you want to remember why that is true is because it would be 0 minus this. You could also do 2π minus this angle, and you'll get the same thing. So 0 minus -0.2527 is 0.2527. So to get that quadrant 3 angle that we see, since it's past pi, we would do pi plus 0.2527. And let's see what that becomes. And we get 3.394. So the two other answers we have here from this equation, remember, do not use the negative one because it's not between 0 and 2π. You got to use the 3.394 and 6.031. This is our quadrant 3 angle and our quadrant 4 angle. Right, but ultimately, this isn't too much of a step up. You just gotta, really the only time in this class where we factor anything or are going to use the quadratic formula, but realize that you can do it is important. All right, so I got one more here in this section before we move on to needing to use identities and what kind of things you're going to have to look for. All right, so number 3 here says solve cosine squared of t equals 2 cosine of t plus 1 for all solutions on the interval 0 to 2π. Give your answer accurate to at least 3 decimal places. Right, so once again, I'm going to look at it the same way. I'm going to use x in place of cosine of t just to see what it looks like. So we've got x squared equals 2x plus 1. Right. If you had something like this, you would know we need to get 0 on one side. Because we're hoping we can either factor it, or if not, we will use the quadratic formula. And, you know, anytime I want to get 0 on one side, I really do not like having a negative on the x squared. So I'm going to subtract the 2x and the 1 over. We got x squared minus 2x minus 1 equals 0. All right, now this one has a 1 in front, so you can kind of run through the options. Can we factor this? Can we have two numbers that multiply to -1 and add to -2? The answer to that is no. The only two numbers that multiply to -1 are 1 and -1. Those add to 0. So we cannot factor this. That's why we have that other tool. We need to use the quadratic formula. Now, once again, just like I did with the last time, I'll plug back in, but after we do the algebra step. So I want to use the quadratic formula. And this section is really the only section we use it in the entire class, but it is prerequisite knowledge. I'll write it down as a reminder and then use it. So we got x equals -b plus or minus the square root of b squared minus 4ac all over 2a. b is -2, so we got 2 plus or minus the square root of -2 squared minus 4. A is 1, c is -1 over 2 times a, which is 1. Okay, and just simplify this exactly like you have in the past. Nothing new here yet. So we got -2 squared is 4. 4 times 1 times negative is +4. I'm just going to keep simplifying it. 4 plus 4 inside the square root is 8. And you can even go as far if you want to simplify the square root. But because 8 is 4 times 2, so we can take a 2 out and leave the 2 inside the square root. The reason I wanted to do that for this one specifically is, you know, one thing that's the main hiccup when using the quadratic formula and solving and simplifying is if these numbers have common factors, or better seen here, then people automatically want to cancel out. But because the plus or minus here, you can't do that. You have to be able to factor it out in all the terms, but now we can. We can take a 2 out of each part. And so we got 1 plus or minus the square root of 2 on top. All right, now what you really want to do here, since we're not done solving, this is going to end up being cosine of t equals this number, is you want to just get the decimal for each of these. Since our answer has to be to at least 3 decimal places, I would go at least 2 spots past it because we're going to do a lot with this number. You might even just go at least 2 or 3 spots further than the answer. Okay, so we got 1 plus the square root of 2, which is going to be something. We'll do it in our calculator, and 1 minus the square root of 2. All right, so let's see what we get. 1 plus the square root of 2 is 2.414214. 2.414214. And 1 minus the square root of 2 is negative of that decimal, negative 0.414214. Right. Now that we've completed the quadratic formula, what you want to do now is plug back in. This is the step I would do it anyway, but you got to remember to do it at some point. X equals cosine of t. Because we're not trying to solve for x, we're trying to solve for t. All right, so we have the two equations. I'm going to organize them like we did last couple of problems and just kind of solve them. I keep writing x, I'm supposed to write cosine of t. Solve them individually. So we're going to have cosine of t equals 2.414. That number. Give us some room there. And then cosine of t equals negative 0.414214. Right, so we've got to solve each one of these. But one thing you want to notice on the left here, we'll see that we can figure this out in our calculator too. But cosine cannot equal 2. It can only be between negative 1 and 1. The cosine of t cannot be anything except between negative 1 and 1. Right, meaning this is going to have no solutions. Now, it doesn't mean our final answer does, it's just this half of our equation doesn't. But the way we would solve this, if we didn't remember that or just didn't realize it, we would do cosine inverse of each side. If you try to do cosine inverse of 2.414214, you will get an error. You're going to get an error because it cannot be that big. Your calculator's not broken. It's just supposed to happen. Now, some people will say you get no real solutions. We haven't talked about any type of imaginary numbers in this class, and we won't. If you get an answer, it's going to have an I in it, and it's probably because you have this selected right here. Make sure you have real selected, right? Because there are imaginary answers, but we do not care about those. Right, but for this one over here, cosine of t equals negative 0.414214. This is between negative 1 and 1, and if you're just not sure, just use your calculator for the first step anyway. One thing you want to point out, this is going to have solutions because it's between negative 1 and 1. And cosine is negative in quadrants 2 and 3. Okay, so we're going to go ahead and draw the picture out. And use our calculator like we do to figure out the first one and use that to figure out the second one. We would do cosine inverse of each side. And we get t equals cosine inverse of negative 0.414214. Let's go ahead and put that in our calculator. And we get 1.9979. Right, remember this is a t value, so it doesn't need to be between negative 1 and 1. 1.9979. It can be absolutely anything. All right, but this is our angle in quadrant 2. It's between pi over 2 and pi. And other reasons why it's in quadrant 2. The other quadrant cosine is negative in is in quadrant 3. And we figured out that angle by doing our reference angle stuff. So we figure out our reference angle once again, the same way we've done probably 50 times in these videos by now. We've got pi minus 1.9979. And we get 1.1437. 1.1437 is our reference angle. And that tells us that the angle that we get in quadrant 3 is going to be pi plus that. And finally, to finish up this problem, pi plus 1.1437, we get 4.285, rounded to 3 spots. Right, so we do have 2 answers here. You don't want to write no solutions or D and E comma this, because these are the only 2 answers. We got 1.998 or 1.9979 if you want to leave it rounded to 4 spots, and 4.285. But one thing like I mentioned before, you want to be really careful with, if you type this in your calculator to get the decimal approximation, you have to go a lot further than where your final answers are going to be. If you want to be super safe, I know not everyone's calculators can do it, but if you want to be super safe and you have this kind of calculator, you can just scroll up and highlight it, or just type in that whole thing to be extremely safe. All right, but that is the basics of solving trig equations by factoring or use the quadratic formula, what things you need to look out for. The next section, we are going to be looking at solving trig equations using identities. Now, one thing I kind of have previewed here, which is I'm going to read through, is very important. It's going to explain why we need to use identities at certain points. But the above problems followed a straightforward strategy, meaning to get sine or cosine equals a number without having to use identities. We factored or we used the quadratic formula. So that's what I mean by straightforward. Not that it was necessarily easy, just that it was a straightforward idea. The thing we have to be wary of, which we'll see in the next section, we could have different trig functions, meaning we can have sines and cosines, but not with different powers as well, not like the first one we did. And if we have that, then we're going to have to use identities. And then the other thing we'll notice, you can see on number 1, it's going to be that difference of cosine squared with sine. But we also will see problems where the angle is different, meaning down here we have 2t and t. And that whenever you solve a trig equation, you have to have all your angles the same, which is what the second item here says. And we have an identity for how to make the angle go from 2t to t or something like that. All right, so we want to solve the following equations for the appropriate variable. Give the answers as directed. All right, so we want to solve this first one. Cosine squared of w equals 4 sine of w for all solutions between 0 and 2 pi. Give your answer accurate to 3 decimal places. All right. If you use the idea before with x being cosine of this time w and y being sine of w, it becomes really clear, hopefully, why we have to do this one a little bit differently, because we'd have x squared equals 4y. And now if you get 0 on one side, which is still what we want to do, we still ultimately want to factor or use the quadratic formula. Then we have to, excuse me, if we want to get 0 on one side, what we have to do is subtract the 4y. That's one way to do it. And we get x squared minus 4y equals 0. Okay. We have a mix match of x and y, but we do not have a common factor, meaning we can't factor an x out, we cannot factor a y out. So what we need to do is use an identity to get only x's or y's. Right? If this was x times y, it'd be just like the first one we did today. We could factor out the common factor and go on. But we do not have that. So I want to look back before we plugged in the equation that we're dealing with here, because we don't really have identities if we're looking at just the letters x and y. And I want to think about it, well, if we can get just x's or y's, that's what we're saying is we only want sines or cosines. Okay. So that's something really important. If we have different powers, like we do here, you want only sines or cosines. And you can't switch sine of w to cosine of w, but you do have an identity to switch cosine of w. Cosine squared of w, because that's the Pythagorean identity. And we want to switch cosine squared of w equals 1 minus sine squared of w. Okay. So let's go ahead and do that. This is now, I'm just going to plug it in with the actual sines and cosines, not use the letters right now. We get 1 minus sine squared of w equals 4 sine of w. You know, it kind of makes it look messier, but the important thing here is that we only have sine. So if we were to go through and do this and replace, we would have y squareds and y's, no x squared with a y. We still want to think about factoring. So we want 0 on one side. Or, you know, if we can't factor, use the quadratic formula. And the way we can factor this, or sorry, the way we can get 0 on one side, there's a couple ways to do it. Since I don't like, once again, having negative on the squared part, I'm going to add the sine squared to the other side and subtract the 1. Sine squared of w plus 4 sine of w minus 1 equals 0. Now you can replace this with the sine of w with y, which there's nothing wrong with. I think it's very helpful to do in general. I just had to show you at the beginning why we have to make this switch from cosine squared to sine squared. So if we do that, we get 0 equals y squared plus 4y minus 1. Now this one works out very similarly to the other one in that, you know, if we think about factoring this, the only two numbers that multiply to -1 are -1 and 1. And this is not 0, this is 4. So we've got to use the quadratic formula again on this one. All right, so we use the quadratic formula. We've got y equals negative b, -4, plus or minus the square root of b squared minus 4ac over 2a. Just go through and continue solving. -4 plus or minus the square root of 16 plus 4 over 2. 16 plus 4 is 20. And like you saw last time, we're eventually going to break apart our two numbers here. So if you want to do that at this point, you can. If you want to simplify it more, you can. I'm going to break it apart here and then use our calculator. We got -4 plus the square root of 20 over 2. And we are going to have -4 minus the square root of 20 over 2. Let's type in each one of these calculators and make sure we round far enough, because we're supposed to go to 3 for our final answer. So I'm going to go 6 again. We get -4 plus square root of 20 divided by 2. Gives us 0.236068. And if we do -4 minus the square root of 20, and then you divide that by 2, you got -4.236068. And you might already be thinking back to the last problem and how this is going to work. Now that we have our two numbers, we solve each one. Remember to plug back in y equals sine of t. Or, sorry, not sine of t. We use w in this problem. So we got to solve each one of these. We got sine of w equals 0.236068. And we got sine of w equals -4.236068. Now, for the same reason as last time, this one has no solutions because sine has to be between -1 and 1. And if you do your calculator with the inverse, you'll see that. So there's no solutions for this one. But for the one on the right, it is between -1 and 1. We will have solutions. So I'm going to make our picture. Sine is positive in quadrants 1 and 2. That means we're going to have an answer in quadrant 1. And an answer in quadrant 2. And we solve by start solving by doing sine inverse of each side. We get w equals sine inverse of our decimal here. Sine inverse of 0.236068. We got 0.2383. Which is our quadrant 1 angle. That's in quadrant 1. And we can see that because this is our quadrant 1 angle, it's also our reference angle. Because we would compute it by 0.2383 minus 0, which is the 0.2383. That means our answer in quadrant 2 is pi minus our reference angle. And pi minus 0.2383 is 2.903. Okay, but just like last time, it's just coincidental that the two we did the quadratic formula on, there ended up being the solutions for only one part. It doesn't have to work like that. You can factor and get solutions for only one part. You can use the quadratic formula and get solutions for both parts. I mean, it's even possible to get solutions for neither part, which would be no solutions. So our answers here, 0.2383. Try to make that so it's legible. It's 0.2383 and 2.903. All right, so we've got two more here. The main difference is going to be seen in number 2 here. Number one, we talked about why if you have different powers with different trig functions, you're going to have to make a change with Pythagorean identity. This one is going to have to be changed for a different reason. So this one says solve 7 times sine of 2t plus 5 times cosine of t equals 0. And the reason this one has to be changed is because the angles. And whenever you have a different angle, it's like having different like terms. You cannot do anything about them. But we must make angles the same. Using the identities that we have at our disposal. And it's always going to be easier to make the bigger angle 2t into the smaller angle t. All right, and the formula, the identity for sine of 2t, that is 2 sine of t times cosine of t. Right, now, basically the main reason we can't solve them if there's different angles is because they have different periods. That's one way to think about it. This if we tried to figure out how to factor it with this, it wouldn't be possible because they have different periods. So we want to make all the angles the same. We're going to plug this in. But you'll see what will happen. We got 7 times 2 times sine of t times cosine of t plus 5 cosine of t equals 0. Uh, 7 times 2 is 14. Might as well just simplify that. Right. And what you want to notice about this one here is this looks a lot like the very first one we did in this section. We have a sine and a cosine, but we can factor out a cosine of t. The greatest common factor. Now, 14 and 5 have nothing in common, so you can't do anything about that. But we can factor out the cosine of t, and we get 14 times sine of t plus 5 equals 0. All right, now we set each factor to 0. We got cosine of t equals 0. And then the inside, 14 times sine of t plus 5 equals 0. And we know what angles make cosine 0 on the unit circle. We don't have to use our calculator for that. That's pi over 2 and 3 pi over 2. It is the angles that are on the y-axis. That's where cosine is 0. For solving this one, we want to get the sine of t by itself. We subtract the 5. We get 14 times sine of t equals negative 5, and then we divide by the 14. We get sine of t equals negative 5 over 14. And now it's really up to you what order you go through. This is where I've been making the picture with the quadrants. Sine is negative in quadrants 3 and 4. So if we draw our picture and draw on some sample angles just like that, we'll have an angle in quadrant 4, and we'll have an angle in quadrant 3. Let me just label in the angles here on the axes. But we know how to begin, once again, getting the first one. We've done this a lot as well. We do the sine inverse of each side. We get t equals sine inverse of negative 5 over 14. See, and we're in radians here, 0 to 2 pi. We take our calculator. Sine inverse of negative 5 divided by 14 is negative 0.3652. Oops. All right, which is exactly that quadrant 4 angle. But like we talked about before, this isn't going to be one of our answers, even though it's coterminal to it. To get it between 0 and 2 pi, we add 2 pi. So just add 2 pi to what we just got. And we get 5.918. Rounded to 3 spots. Since that's our answer, we don't have to round that one any further. And then also the reference angle here. That's what we need to figure out our quadrant 3 angle. And we've done this a few times. The reference angle is 0 minus the -1, or you can do 2 pi minus this. But our reference angle is 0.3652. And then lastly, getting the quadrant 3 angle, we add our reference angle to pi. Pi plus 0.3652 equals pi plus 0.3652. We get 3.507. All right, so for this one, we got 4 answers, which we saw before, and we know that is possible. We got pi over 2 and 3 pi over 2. Then on the second one, remember, don't include this one. It's not between 0 and 2 pi. We got our quadrant 3 angle is 3.507, and our quadrant 4 angle is 5.918. All right, so for the most part, we have really covered everything in the section. There is one more, and the main reason I have this one in here is because it deals with the double angle formula for cosine, and I just want to make sure you get started on something like this on the right track. All right, so this one says solve for cosine of 2t equals 4 sine squared of t minus 3 for all solutions between 0 and 2 pi. Now, just like last time, you notice these different angles. We must make both angles t. We want to make it the same and simpler angle. Right. Now, the identity for cosine of 2t, we have 3 of them. That's the one where we have one with a sine squared and cosine squared. We have one for a cosine squared, and we have one for a sine squared. You want to make your choice based on what your equation says. Since we have a sine squared here, you want to use the identity that has sine squared in it only. Right? We don't want one with cosine squared of t because it's just going to mess it up. So the one with cosine of 2t equals 1 minus 2 sine squared of t is what we're thinking about plugging in. All right, so I'm going to go ahead and do that now. Plug that in for cosine of 2t. We've got 4. Then we got 1 minus 2 sine squared of t. And this equals 4 sine squared of t minus 3. We got to distribute the 4 through. And that would really be the first step, no matter what this ends up looking like. So I'm going to distribute that through. We get 4 minus 8 sine squared of t equals 4 sine squared of t minus 3. One thing I'll have you notice here, and I'm going to plug in y for sine of t just like we've done for most of the problems here, is that you only have sine squareds. You only have one power of sine. So you're going to be able to actually solve for sine squared of t and just do the square root. You won't have to factor or get a quadratic, use the quadratic formula unless you really, really want to. But I'm going to be able to explain that better by plugging in y equals sine of t If we do that, we've got 4 minus 8y squared equals 4y squared minus 3. Now, if we get the y squared by itself, we can add 8y squared to each side and add the 3 to the other side. Now 4 plus 3 is 7. These go away. Equals 4y squared plus 8y squared is 12y squared. And the 3's go away. All right, and then, think about if you wanted to solve for y here. We could divide by 12 on each side. So we get y squared equals 7 over 12. And then to go from y squared to y, we do the square root, but don't forget the plus and minus. Okay, so we got y equals plus or minus the square root of 7 over 12. Now this is really a lot like when we would use the quadratic formula. When we would factor it, we would get stuff that we could easily solve for y or x or whichever one we were using, but you got to make sure you plug back in sine of t for y. Okay, so we've got two equations here. We got sine of t equals positive square root of 7 over 12. And we've got sine of t equals negative square root of 7 over 12. I don't know why I made the square root so tiny. Now, like last time, you can get a decimal for this and use that. Since there's not really anything to do here besides just do the inverse, you can just do the inverse at this step if you'd like. And, we kind of talked about before, but if this number is not between -1 and 1, we'll get an error with our calculators. We get t equals sine inverse of the square root of 7 over 12. Let's see what that is. Oops, that is not sine inverse of square root of 7 divided by 12. And we get 0.8691. All right, and I'll talk about the quadrants and getting all the angles in a second. But this one I'll also do the same way. Do the sine inverse of each side. Remember the negatives in this side already, so it goes inside. And then sine inverse of negative square root of 7 over 12. Be lazy here and hit second enter, so the same thing pops up. And then you go on the front and hit second insert, you can put that negative sign. Probably doesn't even save that much time. But we get negative 0.8691. Where's my mouse? There we go. Now we've solved plenty of problems here with sine and cosine. We know really what we're looking at here. Draw a little picture, kind of to split the two, so I don't have to draw two pictures for each one. But this on the left side, sine being positive, this is a positive number. We're going to have positive in quadrants 1 and 2. So I'm going to draw our two angles in that color. And this is our quadrant 1 angle here, 0.8691. And if you want to keep solving for that and you get the other one, the reference angle here, since it's in quadrant 1, is exactly itself. Right, that reference angle is going to be 0.8691 as well. Right, so that means our quadrant 2 angle is pi minus, it's behind pi minus 0.8691. We'll go ahead and type that in. And we get 2.272. So we've got two answers that are going to make up in our final answer here. So far, we've got 0.8691 and 2.272. Now the other side here, sine of t equals a negative number, is going to have an angle in quadrants 3 and 4. And the one we got from the calculator is from quadrant 4, negative 0.8691. And we've done a couple in this section already. We know we have to add 2 pi to this to get it between 0 and 2 pi. So let's do that. We got 5.414. Which is going to be the answer that we're actually going to use. And then that reference angle, you'll actually notice that it's exactly the same as the other reference angle, because it's going to be the positive of this number, 0.8691. Because we would get it by 0 minus negative 0.8691. And then that tells us our quadrant 3 angle here, we're going to be pi plus 0.8691. Oops. Pi plus 0.8691. We got 4.011. And that gives us our other two answers. So we are going to have 4 answers here, just like we have for quite a bit of these. We had 0.8691. We had 2.272. We had 4.011. And we got 5.414. Okay, now one thing that's kind of interesting about this problem, we talked about solving a lot of these equations and we only have one answer, like sine of t equals this, and then we get 2 answers from that. But something we mentioned before about the unit circle is, if your number that you're trying to get is just negative, like sine, where's sine 1/2 and where's sine negative 1/2? They all have the same reference angle. And it's no surprise when we actually went through and figured out actually solving and getting the 4 answers that everything had the same reference angle, because we were solving where sine equals this number and sine equals negative this number. Now, as you see, we didn't really mention that at the beginning. It's not something you have to memorize at all, but if it's something you recognize on a problem and you want to use it, you can definitely use it. But the one thing to keep in mind, as we've done all the rest of the problems, is that you only have 2 quadrants where it's a particular number. So don't accidentally start adding in answers that aren't really there in your question. All right, but this is section 3.3. Plenty of practice here. There shouldn't be any type of issues working the homework as far as not having a question like this. And one thing I would say you saw based on everything we did in this section was the first half we saw how everything was really just one more step of what we did and 2.3. And then the second half, we use an identity to turn it into something of the first half. So it's very progressive in how it builds up. That's, you know, exactly how you want to think about these problems. As even though they are long, you know, something like this was really plugging in an identity and factoring, solving square roots, whatever we had to do. And it turns into a 2.3 problem.